Now that we've examined what a fast Fourier algorithm looks like on a polynomial, let's look at what it can do to signals. Today we're going to be looking at fast Fourier transforms. Now in the last lecture, we looked at the polynomial representation, and we're going to use some similar principles that we learned there, the roots of unity representing our fundamental frequency, and the even and odd split to simplify the overall equations. So, why is this so important? Well, comparing the number of calculations of the DFT versus the FFT really allows us to simplify what we have to do in order to transmit data. So DFT requires n squared calculations, where n is the number of sample points, where the FFT requires n times log n number of points. Now, at low numbers, it doesn't impact it too much, but when you get to magnitudes such as like 10 to the 9, then you're really comparing numbers at that point, because then you have 10 to the 18 number of calculations, which is a lot, versus only 9 times 10 to the 9, which is a huge difference for a computer. So let's pretend we have some signal, and then we have it sampled x1, x2, x3, up to xn. For the cases of this explanation, I'm going to talk about n as though we're 1024. Now you're typically going to want your n to be power of 2, so 2, 4, 8, 16, so on. And you have all these sample points, and we want to calculate the complex Fourier coefficients. So is there a way for us to do that? Well, there is. We learned the calculations last time. We learned the formulas in our last lectures in 327, where the complex Fourier coefficient k is equal to the sum fj e to the negative I 2 pi over n times jk, starting at j equals 0, going to n minus 1. And you can reverse that by swapping fk and the complex root, and the complex coefficient, multiplying it by 1 over n, and the equation in pink you see there. And if you take a look at it, you realize that both equations use e to the negative 2 pi I over n. So you sort of define that as our fundamental frequency. And then if we keep going from there and expand the process, we can realize that we can make an entire matrix and describe it using just omega n, or the fundamental frequency. So that's what we're looking at here, the DFT matrix. So this simplifies all of our multiplication into a matrix form. And if you look here, it's really easy to see how it's n squared number of calculations, right? You have f0 all the way down to fn times an n by n matrix. And so it's n for the first row, n for the second row, all the way up n times. So it's really easy to see why there's so many calculations involved. And so what we're wondering here is there any way to make this calculation faster? And there is, luckily. This identity here, with a complex coefficients equal the matrix described before of f1024 times the sampling points, equals two identity matrix stacked on top of each other with negative diagonal matrix filling up the other column, multiplied by two matrix, f512 times f512, which would be the same matrix as before, only smaller, where also being multiplied by a 2 by 1 matrix with the f even components and the f odd components. So this top one would be f0, 2, 4, 5, those sampling points, and f odd would be 1, 3, 5, and so on. So this limits our number of calculations greatly, as you can see by having those zeros in there. You took a 10 by 24 matrix, a 1024 matrix, and split it to the point where half of those values are equal to 0. And obviously anything multiplied by 0 is 0, which simplifies the calculations greatly. Now, this is really good already, but can we do better? The answer is we can. This works because we can just keep shrinking, so 1024 to 512, 512 to 256, 256 to 128, and so on, all the way down to f2. And this really reduces the number of calculations required. If you simplify this whole process, it equals n log n calculations, which I talked about in the beginning. And this will allow us to greatly speed up the calculation time. Now, as I talked about earlier, we can compare n log n calculations versus n squared. And when you're operating at factors such as 10 to the 9, which you do for image compression, audio compression, and data transmission, you really get to see why this works so well, and why these fast calculations allow you to do so much. So, for the next lecture, we're going to talk about practical applications using MATLAB of denoisifying a signal. Thanks.